Hey folks, welcome back. In this video we're going to go over paper 1, i.e. the multiple choice questions from the 2018 Specimen SQA Higher Physics exam paper. Now there are 25 questions in this paper and I recommend that you try them yourself before looking at these solutions. So let's get started. Question 1 says that the following velocity time graph represents the vertical motion of a ball. So we have velocity in meters per second on the y-axis and time in seconds on the x-axis, and you'll see the velocity starts off at 19.6 meters per second, it then reaches 0 meters per second after 2 seconds, and then after another 2 seconds it reaches minus 19.6 meters per second. The question then says which of the following acceleration time graphs represent the same motion. So we simply want to determine the corresponding acceleration time graph for the velocity time graph that we were given. So we can see we've got an acceleration sloping up the way, down the way, constant negative acceleration, and then we've then got these kind of stepped patterns here. So looking back at the velocity time graph that we're given, notice that the graph shows a uniform deceleration, because remember on a velocity time graph, a line sloping down the way represents a uniform deceleration. So on an acceleration time graph, this will be a constant negative acceleration. And because the graph is based on the vertical motion of the ball, vertically the ball is going to have gravity acting on it, so it's going to have acceleration due to gravity acting on it vertically, which means that the acceleration value will be negative 9.8. So looking at our graphs here, the only one showing a constant negative acceleration is C. Question 2 says a train accelerates uniformly from 5.0 meters per second to 12.0 meters per second while travelling at a distance of 119 meters along a straight track. The acceleration of the train is. Well, notice the question gives an initial speed, a final speed, a distance, and we're asked for an acceleration. So this is dealing with equations of motion here. So we're going to write down suvat in order to find out which equation of motion we need to use. So we know the displacement or distance s is 119 meters. We know that the initial speed u is 5.0 meters per second. The final speed v is 12.0 meters per second. The acceleration a is what we're being asked to find, and the time is something we don't know. So I'm going to put a star next to a because that's the one we're trying to find. And this means we're going to use the equation of motion that doesn't have t in it. So looking at your relationship sheet, that one will be v squared equals u squared plus 2as. Let's sub in the numbers and rearrange to find what a is. So we have 12.0 squared equals 5.0 squared plus 2 times a times 119. So doing the 12 squared, we get 144, minus the 5 squared means minus 25, and then we can do 2 times 119a on this side to get 238a equals 119, and then dividing both sides by 238 gives us a equals 0.5 meters per second squared, so this means the answer is A. Question 3 says two blocks are linked by a Newton balance of negligible mass. The blocks are placed on a level frictionless surface. A force of 18.0 newtons is applied to the blocks as shown. So we've got our 4 kilogram block linked to this 6 kilogram block as a system through this Newton balance, and then we've got a pulling force of 18 newtons to the right. It then says the reading on the Newton balance is. In other words, we're being asked to calculate the tension here in the Newton balance due to the 4 kilogram block. So the strategy for this is that we first need to determine the overall acceleration of the system. So we're going to use F equals ma once to do this, and then we need to use F equals ma again in order to find the reading on the Newton balance. So using Newton's second law, F equals ma, we're trying to find the overall acceleration of the system first of all. So we have A equals F over m. Substituting in the numbers, we have 18 newtons applied to the system, so that's 18 divided by 6.0 plus 4.0, which is the mass of the whole system, i.e. the 4.0 kilograms plus the 6.0 kilograms. We've just added the masses together there, and then doing 18 divided by 10 in your head or in a calculator should give you 1.8 meters per second squared. However, we're not finished because we only know the acceleration of the system just now. We don't know the tension or force in this part of the Newton balance due to the 4 kilogram mass. So now we want to calculate the force acting on the 4 kilogram block. So we can use F equals ma again. So we have F equals ma, and then substituting in the mass only for the 4 kilogram block this time is 4.0 times the 1.8 for the value we just calculated, and then putting that into your calculator should give you an answer of 7.2 newtons, and this is the option B. Question 4 says a block of wood slides with a constant velocity down a slope. The slope makes an angle of 30.0 degrees with the horizontal as shown. The mass of the block is 2.0 kilograms. So we've got our 30 degrees for the slope here and our 2 kilogram block which is moving down the slope. It then says the magnitude of the force of friction acting on the block is. Well, firstly we need to notice these key words, constant velocity. So since the block is moving at a constant velocity, the component of weight down the slope will equal the frictional force up the slope, i.e. we'll have balanced forces. So basically, to find the frictional force acting up the slope, we just need to find the component of the weight down the slope. And remember that is given by the expression mg sine theta. So we can say F friction equals mg sine theta, which equals the mass 2.0 times gravitational field strength on Earth 9.8 times sine of 30, which is equal to 9.8 newtons. So this is the answer C. Question 5 says the diagram shows the masses and velocities of two trolleys just before they collide on a level bench. So we've got this trolley of 1 kilogram moving at 6 meters per second to the right, and this stationary trolley of 2 kilograms at 0 meters per second. It says after the collision, the trolleys move along the bench joined together. The kinetic energy lost in this collision is... Well, first of all, if the trolleys are joining together, that suggests it's going to be an inelastic collision, which means that there probably will be some kinetic energy loss, so it's probably not going to be this 0 joules value here. So to answer this question, we first need to determine the final speed that both trolleys move off at. So this is a conservation of momentum question. So we have total momentum before equals the total momentum after, and then we can write down our expression in symbol form, which is m1u1 plus m2u2 equals m1v1 plus m2v2. And since both trolleys are joining together after the collision, we can simplify this right-hand side expression. So we can say m1u1 plus m2u2 is equal to m1 plus m2 times v, and we can factorise that there because v1 and v2 will be identical. So subbing in the numbers now, we have 1.0 times 6 for this part, plus 2.0 times 0 for this part is equal to 1.0 plus 2.0 for the two masses times v. So obviously this one will cancel out because it's times by 0, and then simplifying both sides, we have 3.0v equals 6.0, and divided both sides by 3.0 gives us v equals 2.0 meters per second. Now that we have the velocity that both objects move off at, we now need to calculate the kinetic energy before and after the collision, and then we need to compare these values in order to see how much kinetic energy has been lost. So before the collision, we have EK before equals a half m1u1 squared plus a half m2u2 squared, which equals a half times 1.0 times 6.0 squared plus a half times 2.0 times 0 squared, just using our values from the question. And putting that into your calculator should give you an answer of 18 joules. And then we can do the same for after the collision, so EK after equals a half m1v1 squared plus a half m2v2 squared, which equals a half times 1.0 times the 2.0 squared, that was our final velocity we just calculated, plus a half times 2.0 times the 2.0 squared. Putting that into your calculator should give you an answer of 6 joules. So lastly, we need to find the difference between the two kinetic energy values. So we have EK lost equals 18 minus 6, which equals 12 joules. So there was a lot of work there required just for 1 mark for a multiple choice question, but we can say the answer is C, 12 joules. Question 6 says the graph shows the force that acts on an object over a time interval of 8.0 seconds. So we have force in newtons on the y-axis against time in seconds on the x-axis, and it says the momentum gained by the object during the 8.0 seconds is. Well, that's the total time for this graph, the 8.0 seconds, and we need to notice the wording here, momentum gained. That is talking about a change in momentum. And the key thing here to be aware of is that impulse is equal to the change in momentum. So we're basically just being asked here to find the impulse from a force time graph, but they're just doing it in a roundabout way. So remember, impulse is equal to the area under a force time graph. So if we want to find the total area under this big thick line, then it probably helps to split this graph into shapes. So we've already got a rectangle here, but if we use a wee dash line here to separate this part, then that gives us another rectangle and a triangle. So these are easy shapes that we'll be able to calculate the area of. So let's now label this area as 1, this area as 2, and this area as 3. And we can say the area is equal to length times breadth for this rectangle plus length times breadth for this rectangle plus a half times base times height for this triangle. So substituting in the numbers now, we have length times breadth, so that's going to be 4.0 times the 4.0. Again, this is identical, this rectangle, because going from 4.0 to 8.0 is another length of 4.0 times the 4 for the height there. And then for the triangle, we have a half times the base, which again goes from 4 to 8, so that is 4 there, times the height, which goes from 4 up to 10, so that is 6. So that's a half times 4.0 times 6. And putting that all into your calculator gives you an answer of 44 kilogram meters per second, which is the answer C. Question 7 says a javelin is thrown at an angle of 60.0 degrees to the horizontal with a speed of 20.0 meters per second. And you're shown that in the diagram here. It says the javelin is in flight for 3.5 seconds. The effects of air resistance can be ignored. the horizontal distance travelled by the javelin is? Well, this is a projectile question for an object launched at an angle, and because we want to find the horizontal distance travelled by the javelin, also known as its range, then we want to use the data given to find the horizontal component of the initial speed. So remember, the horizontal component is given by cosine because cos goes across. So this will be cosine 60 or cos 60. So in order to find the horizontal component of the initial speed, we have UH equals 20.0 cos 60, which equals 10 meters per second once you put it into your calculator. And now we can use suvat for the projectile in order to work out what values we have and what values we're trying to find. So for the horizontal motion, we're trying to find what S is. We know the initial horizontal speed is 10 meters per second. We don't know what the final horizontal speed is. We know the acceleration A is 0 meters per second squared. And we know the time of flight is 3.5 seconds. Remember, the time of flight for a projectile to travel vertically is going to be identical to the time of flight for a projectile to travel horizontally. So we can use that time here, and we could also use it in vertical motion as well. And I've also said that acceleration is 0 here because remember, horizontally there is no acceleration. It's only vertically that there will be an acceleration. So let's put a star next to S because that's the one we're trying to find. And because we don't know what V is, let's use the equation of motion that doesn't have V in it. So that's going to be the equation S equals ut plus a half at squared from the datasheet. And let's now sub in the numbers. So we have 10 times 3.5 plus a half times 0 times 3.5 squared. And you'll notice that this term cancels out because it's times by 0. And this means that the more savvy amongst you would have realised that you could actually just use the speed distance time equation, S equals ut or D equals vt, in order to find this distance. Because remember, the equation will always simplify to speed distance time for horizontal motion. But I've just shown you that this will actually be the case by subbing in the 0 here. So 10 times the 3.5 gives us 35.0 metres, which is the answer B. Question 8 says two small asteroids are 12 metres apart. The masses of the asteroids are 2.0 times 10 to the 3 kilograms and 0.050 times 10 to the 3 kilograms. The gravitational force acting between the asteroids is. Now notice we're given two masses, a distance, and we're asked to find the gravitational force. So this is dealing with Newton's law of universal gravitation, which is F equals gm1m2 over r squared. And we want to calculate F. So let's sub in the numbers here. So we have 6.67 times 10 to the minus 11 for the universal constant of gravitation g, which you'll find on the datasheet, times 2.0 times 10 to the 3 for the first mass, times 0.05 times 10 to the 3 for the second mass, divided by 12 squared, which was the distance given. Now we can put that into our calculator, not forgetting to square the bottom term there, and you should get an answer of 4.6 times 10 to the minus 8 newtons, which is the option B in this case. Question 9 says a spaceship on a launch pad is measured to have a length L. This spaceship has a speed of 2.5 times 10 to the 8 meters per second as it passes a planet. Which row in the table describes the length of the spaceship as measured by the pilot in the spaceship and an observer on the planet? So you can see the options here for the length measured by the pilot in the spaceship and by the observer on the planet. We have L, greater than L, and less than L. Well, this really just comes down to knowing the definition of length contraction, or the difference between proper length and contracted length. So remember, when you're in the frame of reference of an object and you measure the length of that, then you're going to measure the proper length L. So the length measured by the pilot in the spaceship is going to be L. So that means we can rule out D and E. So we're looking at A, B, or C as our answer here. And the length measured by an observer on the planet, they're going to be measuring the contracted length, which means the length is going to appear smaller than the proper length. So it's going to be less than L. So this means our answer is C. Next we have question 10, which says the siren on an ambulance is emitting sound with a constant frequency of 900 Hz. The ambulance is travelling at a constant speed of 25 meters per second as it approaches and passes a stationary observer. The speed of sound in air is 340 meters per second. Which row in the table shows the frequency of the sound heard by the observer as the ambulance approaches and as it moves away from the observer? Well, this is a Doppler effect question, and there's several ways you could approach this. One is by using the equation for the Doppler effect and plugging the values in order to work out the actual values here, or we could just think about it a bit more. Because we've got the frequency of the source being 900 Hz, we're going to think about this in terms of this 900 Hz. So first of all, for the ambulance approaching, we can say that as the ambulance approaches, more wavefronts reach the observer each second, and this means they're going to experience a higher frequency than the 900 Hz. So I'm looking at a value of 971 in this case, because that is the only option higher than 900. So I'm going to eliminate A, C and E here and look at just options B and D. But I want to find out what's going to happen to the frequency. Is it going to get lower as the ambulance moves away, or is it going to stay the same at the 900? Well, in the opposite way, we can say that as the ambulance moves away, fewer wavefronts reach the observer each second. So this means they're going to experience a smaller frequency than the 900 Hz for the sound source. So we can say that the only smaller value is 838. So we have 971 and 838 being our answer, which gives us B. Question 11 says cosmic microwave background radiation and Olber's paradox provide evidence for the photoelectric effect, the Bohr model of the atom, the theory of special relativity, the Big Bang theory, or Newton's law of universal gravitation. Well, you should remember that CMBR, cosmic microwave background radiation, and Olber's paradox provide evidence for the Big Bang theory. Question 12 says a student makes the following statements about particles in electric fields. Statement 1 says a neutron experiences a force in an electric field. Statement 2 says when an alpha particle is moved in an electric field, work is done. And statement 3, an electric field applied to a conductor causes the free electrons in the conductor to move. Which of the statements is or are correct? Well, let's look through each statement in turn and decide which ones are true or false. So first of all, a neutron experiences a force in an electric field. That is going to be false. So that's because a neutron, remember, has no charge or a neutral charge, which means it's not going to be affected by charged plates between which an electric field exists. Statement 2, when an alpha particle is moved in an electric field, work is done. Well, that is going to be true because it doesn't matter what charged particle it is, as long as the particle has charge, it's going to require work being done to it in order to move it, i.e. it's going to require a force applied to it in the field. And remember, work done is an energy, so energy is needed to move the charged particle in the field. And statement 3, an electric field applied to a conductor causes the free electrons in the conductor to move. That is also true because electrons, remember, have a negative charge and they're going to be attracted or repelled away from positively or negatively charged plates. So therefore we have 2 and 3 are correct, which gives us the answer D. Question 13 says the electric field patterns around charged particles Q, R and S are shown. Which row in the table shows the charges on particles Q, R and S? So we can see that charge Q is a point charge, and then we've got charges R and S which are near each other. It then says which row in the table shows the charges on particles Q, R and S. Well, looking back at the picture, you should remember that field lines will always go in the direction that a positive charge would move if placed in that field. So if you brought in a positive charge close to a positive charge, it would be repelled away from it out the way. So this charge Q must be positively charged. So looking at the table, that means our answer is going to be B or E. And then looking at charges R and S, again the same rule applies that the field lines will move in the direction that a positively charged particle would move if brought close to that field. So if we brought a positively charged particle here and let it go, it would move in towards charge S, and if we brought in a positively charged particle, it would be repelled away from charge R. So this suggests that R is going to be positively charged and S is going to be negatively charged. Another way of thinking about this, remember, is that field lines always go out of positive charges and into negative charges. So we've got positive, positive and negative. So here in the table we can see positive, positive and negative, so the answer is B. Question 14 says a student makes the following statements about an electron. Statement 1 says an electron is a boson, Statement 2, an electron is a lepton, and Statement 3, an electron is a fermion. Which of these statements is or are correct? Well, this just relies on you knowing the breakdown of the standard model. So first of all, an electron is a boson. Well, that is false because remember, the force-mediating particles or force-carrying particles, they are the only particles that are bosons in the standard model. An electron, on the other hand, is a type of lepton, so that is true. And an electron is a fermion, that is also true because remember, fermion is just another name for a matter particle. And you should remember that there are 6 types of leptons, the electron, muon and tau particles, as well as their corresponding neutrinos. So we have statements 2 and 3 are correct here, which is the answer E. Question 15 says the last 2 changes in a radioactive decay series are shown below. A bismuth nucleus emits a beta particle and its product, a polonium nucleus, emits an alpha particle. So we have our bismuth nucleus undergoing a beta decay to give us polonium, and then this polonium nucleus undergoing an alpha decay to give us lead. Well, to answer this kind of question, we need to start at the end and work backwards, because we're given the mass number and the atomic number at the end, but we don't know any of the other numbers. So because polonium is undergoing an alpha decay to get to lead here, then this means that working backwards, if the mass number is 208 over here and it's undergone an alpha decay, then that means R must have decreased by 4 to get to here, because remember, an alpha decay removes 4 from the mass number and 2 from the atomic number. So R will decrease by 4 and S will decrease by 2. So this means we need to add 4 to the 208, so we get 212. And then for 82, we need to add the 2 going backwards. So we get 84 there. And we can see we now know R and S, so that's 212 and 84. So the answer could be either D or E just now. So we need to work backwards again to get P and Q. So for beta decay, the mass number there, the upper number, is going to be unchanged. So that's going to be 212 as well. And in beta decay, remember, the atomic number is going to gain 1. And that's because a neutron with neutral charge is converted into a proton. And remember, protons are positively charged. And so you're going to gain 1 to the number of protons, which is the atomic number. So that's going to gain 1 going from here to here. So if we're working back the way, then we need to subtract 1 from 84 to get 83. So that means I have 212, 83, 212 and 84. So that gives me the answer D. Question 16 says light from a point source is instant on a screen. The screen is 3.0 meters from the source. The irradiance at the screen is 8.0 watts per meter squared. The light source is now moved to a distance of 12 meters from the screen. The radiance at the screen is now. So notice we're given an initial irradiance, we're being asked to find a final irradiance, and we know an initial and a final distance. So we're going to use the relationship between irradiance and distance from a point source. So we have I1 D1 squared equals I2 D2 squared. Subbing in the numbers gives us 8.0 for the initial irradiance times 3.0 squared for the initial distance is equal to I2, the final irradiance, times 12 squared for the final distance. And then putting into your calculator and rearranging for I2, we get I2 equals 0.5 watts per meter squared, which is option A. Question 17 says S1 and S2 are sources of coherent waves. An interference pattern is obtained between X and Y. So there's X, there's Y, and there's our two sources S1 and S2. And we've got a central maximum at this point, and then labels P, Q and R, which are also going to be other maxima because they're separated the same distance apart. The first order maximum, it says, occurs at P, where S1P equals 200 millimeters and S2P equals 180 millimeters. For the third order maxima R, the path difference S1R minus S2R is. Well, notice how we're given some data in terms of the point P, but we're asked about the path difference with regards to point R. So we're first going to find the wavelength using the P data, and then we'll use that wavelength in the R data to find the path difference. So remember, for maxima, we can say path difference equals m lambda. Let's rewrite the path difference in terms of the S1P and S2P. So we have S1P minus S2P equals m lambda, or in other words, 280 minus 180 equals 1 times lambda, using m equals 1 for P there because m equals 0 is the central maximum, remember, so one maxima along has to be m equals 1. And notice how I've also kept the path difference in terms of millimeters, so that just means my wavelength will also be in millimeters. So I have lambda equals 20 millimeters, and now that I know the wavelength, I can plug this into my path difference for point R. So we have path difference equals m lambda, again for this maxima. So S1R minus S2R equals m lambda. And remember, this is the third order maximum, so m equals 3 in this case. So this is equal to 3 times the 20, which we found out earlier, which is going to be 60 millimeters. So that gives us the answer E. Question 18 says, in an atom, a photon is emitted when an electron makes a transition from a higher energy level to a lower energy level as shown. So here you've got the electron falling down to a lower energy level, and you're given the energy levels there, and it shows that it emits a photon. The wavelength of the radiation emitted due to an electron transition between the two energy levels shown is. Well, remember, we've got an expression for change in energy levels depending on frequency. That's delta E, or E2 minus E1 equals HF. But you might remember that we can form another equation in terms of wavelength for this. So we can say that delta E equals HF equals HC over lambda, where all I've done there is replace the frequency in this equation with F equals V over lambda from the wave equation, V equals F lambda, and I've also replaced the V symbol with C because we're dealing with light here, so C is the speed of light. So we've got delta E, or E2 minus E1 equals HC over lambda, and we can then plug in the numbers. So remember, for the change in energy, we take the upper energy level and subtract the lower energy level here. So we have minus 5.4 times 10 to the minus 19 minus 21.8 times 10 to the minus 19, which will give us a plus in there, so this will be a positive energy, is equal to 6.63 times 10 to the minus 34, which is Planck's constant H from the datasheet, times 3 times 10 to the 8, which is your speed of light, again from the datasheet, divided by the wavelength lambda. Now what I can do is just plug these numbers into my calculator, and then I can cross multiply to get lambda over this side. So I do this thing in the numerator divided by this answer here to get an answer of 1.21 times 10 to the minus 7 meters. And you'll see that gives me the answer C here. Question 19 says a ray of red light travels from air into water. Which row in the table describes the change, if any, in speed and frequency of a ray of red light as it travels from air into water? Well, if we're going from air into water, then that's going from a less dense material into a more dense material. So we know that the light should slow down when it does that, i.e. the speed decreases. So we're looking at D or E as an answer here. And then for frequency, you should remember that when light goes from one material to another, frequency always stays the same. So as frequency stays constant, it means our answer is going to be D here. Next we have question 20, which says the RMS voltage of the main supply is 230 volts. The approximate value of the peak voltage is... Well, writing down our equation relating RMS and peak voltage, we have VRMS equals V peak over root 2, and you can either then sub in or rearrange. So I'm going to rearrange for V peak. So let's multiply the root 2 by the VRMS there to get V peak equals root 2 VRMS, and substituting in the numbers gives us root 2 times the 230, and putting that into your calculator should give you an answer of 325 volts, which is the option C. Question 21 says an oscilloscope is connected to the output terminals of a signal generator. The trace displayed on the screen is shown. So we can count how many full waves we have here. We have one full wave and then two full waves there, and these boxes are the divisions shown. The time base of the oscilloscope is set at 30 milliseconds per division, and the frequency of the output signal from the signal generator is... Well, remember, to find frequency, we need to find the period first. So to find the period, remember we're dealing with the x-axis or the horizontal axis on this display, and remember we count the number of divisions for one wavelength, and we multiply this by the time base setting. So we can say that t, the period, is equal to the 4 divisions for one wave, times 30 milliseconds per division, and you'll notice that because we have divisions times 1 over divisions, the division values will cancel out. So we end up with 4 times 30, which is 120 milliseconds. Now I'm just going to rewrite this in terms of seconds because that's going to help me in a minute when I do the frequency. So this is the same as 120 times 10 to the minus 3 seconds. And now to find the frequency, remember period and frequency are related through t equals 1 over f. So let's rearrange for f to get f equals 1 over t. And now we can sub in the period to get 1 over 120 times 10 to the minus 3, which if you put into your calculator should give you an answer of 8.3 Hz. And you'll see that is the option E. Question 22 says in the diagrams below, each resistor has the same resistance. Which combination has the least value of the effective resistance between the terminals X and Y? So firstly, this phrase effective resistance might be throwing you off, but effective resistance basically just means total resistance. Or another way to think about it is, imagine you were to take these 4 resistors here and combine them into just one equivalent resistance. That's basically what it means. However, you should be aware that total resistance will be the smallest for resistors in parallel, and the opposite is also the case, so the total resistance will be the largest for resistors in series. So C, for example, will give the largest possible resistance, whereas A is going to be the correct answer for us because that gives the smallest possible resistance. Moving on, we have question 23, which says 4 resistors, each of resistance 20 ohms, are connected to a 60 volt supply of negligible internal resistance as shown. So we've got a 60 volt supply and then 4 20 ohm resistors, with 2 of them being in parallel. The potential difference across PQ is... Well, notice between P and Q we only have these 2 parallel resistors of 20 ohms each. But in order to find the potential difference, it's going to help to find the total resistance of this combination first. So you can do this in one of 2 ways. You can either use the equation for resistors in parallel, or you can use the trick to identify that these 2 resistors are identical. So if we do the equation first of all, you can see that 1 over RT equals 1 over R1 plus 1 over R2. Subbing in the numbers, we get 1 over 20 plus 1 over 20, which simplifies to 2 over 20. And then we need to swap both sides. So we get RT equals 20 over 2, which is 10 ohms. So that means we could think about this combination as just being one resistor with a value of 10 ohms. And the quicker way to arrive at that answer, remember, uses the trick, which says that whenever the resistors in parallel have identical values, then you can take the value of one of them and divide by how many resistors there are. So we could take 20 there and divide it by 2 because there's 2 resistors to give us the 10 ohms. But remember, that only works when the resistors have the same value. So to be safer, I've used the equation here, so that's 10 ohms, and then I'm going to find the total resistance because I want to find the total current in this circuit. So total resistance RT is going to be R1 plus R2 plus R3, so that's the 20 ohms there, plus the 10 ohms that I've just worked out for this combination, plus the 20 ohms there. So this gives me 50 ohms in total, and I've got 60 volts supply, so let's find the total current in the circuit, and then I can use V equals IR to find the voltage across this section. So using V equals IR first to find the total current, we can do VS equals IT RT, where VS is the supply voltage 60 volts, IT is our total current, which we're trying to find first of all, and RT is the total resistance that we've just worked out. So we have IT equals VS over RT if we rearrange, and then subbing in the numbers, we get 60 over 50, which is 1.2 amps. And lastly, we just need to use V equals IR again to find the voltage across PQ. So we can say VPQ equals IT times RPQ, because the total current will be flowing through this. So remember, we found the resistance combination here to be 10 ohms, and we now know the current that's going to be flowing through that 10 ohm resistor. So we have 1.2 for the current times 10 ohms, which gives us 12 volts. So the answer here is A. Question 24 says the EMF of a battery is the total energy supplied by the battery, the voltage lost due to the internal resistance of the battery, the total charge that passes through the battery, the number of coulombs of charge passing through the battery per second, or the energy supplied to each coulomb of charge passing through the battery. Well, this is simply just a definition, so you should know your definitions, and this is the one for EMF, the electromotive force. And remember, EMF has the exact same definition as voltage or potential difference from National 5. And this is that the EMF of a battery is the energy supplied to each coulomb of charge passing through the battery, so the answer is E. Lastly, question 25 says a student carries out 3 experiments to investigate the charging of a capacitor using a DC supply. The graphs obtained from the experiments are shown. So we have graph 1, graph 2 and graph 3. The axes of the graphs have not been labelled. Which row in the table shows the labels for the axes of the graphs? So let's just look at the options. So we have voltage and time, current and time, and charge and voltage. Well, looking back at the picture, remember for the charging of a capacitor, the potential difference or voltage across the capacitor is going to increase from 0 over time up to a maximum value. So that is going to be doing that in an exponential curve like this one here. So graph 1 must be the voltage and time graph. We should also know that for a charging capacitor, the current will start off at a maximum value and decrease over time exponentially, just like graph 2 shows here. So graph 2 must be the graph for current and time. And that leaves graph 3 here, which shows the relationship between charge and voltage, or charge and potential difference for a capacitor. And remember, charge and voltage are directly proportional for a capacitor, so that is the graph shown here, the straight line going through the origin. So we have voltage and time for graph 1, current and time for graph 2, and charge and voltage for graph 3, which means my answer is going to be D here. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.